So this afterglow theory have been proposed by many people that how we can understand the afterglow properties of the GRB. And if you see this slide where an afterglow theory, afterglow forward shock model has been shown that how it might look like. And this theory was given by Sari Piran and Narayan back in 1998. Uh, that how the spectral energy distribution of a GRB might be, assuming the synchrotron radiation. Uh, the energy distribution of the injected electrons are shown in this figure. Two cases are shown where the spectral energy distribution, this spectral energy distribution is non-thermal, and it's a function of the electron energy index P of the injected electrons, and the different segments of this spectral energy distribution are function of three break frequencies, which are function of uh, time, and with time these break frequencies are evolving, and that's what giving the evolution of the spectrum. And this is the most uh, uh, this is the most typical afterglow spectral energy distribution which have been observed in many cases. It's also possible that if you see the left hand side of this figure, uh, that if the observer is not sitting on axis, then the observer will not be able to see the full jet, and in that situation, if the observer is off axis, then the observer will not be able to see the effect of the jet in one go, but he will be able to see that effect of the jet in due course of time, and that will give rise to a different effect. That's called off-axis emission. It's also possible that throughout the jet, the energy distribution is not constant, but there is an angular distribution of energy throughout the jet, and that will also cause the outflow to be structured, and in that case also the observed effects will be somewhat different, and that both the scenario, they will give rise to rising afterglow in the light curve, and it also tells a lot of other information about the nature of the emission. Here is a very good example of a GRB back in 2002, where you see that how the afterglow is behaving. So if you see the spectral energy distribution, the simulated observed spectrum compared with the theoretical model, and you see that how spectral energy distribution is evolving with due course of time, and the peak of spectrum is shifting more towards lower frequencies as the break frequencies are evolving with time. And the modern light curve with different colors are also shown in the leftmost panel, and they are similar to what has been shown in this simulated spectrum, but in the temporal domain. And some of the forward shock features recently seen by Swift satellites are in XRT, and in XRT, after the gamma ray emission is over, the XRT light curve shows a very steep decay in the light curve, and then possibly a bump, and then the typical decay of 1 or 2, and then the jet break. These kind of features have been seen approximately in 1/3 of the GRBs. That's called a canonical XRT afterglow light curve. This kind of canonical XRT light curves have been shown after the Swift, and they tell a lot about the nature of the central engine and what kind of progenitor might be. And this has been very useful to know more about the nature of the progenitors. In pre-Swift era, we were able to know more about the jet brakes more oftenly than what we do now with the advent of Swift and of Swift. We have seen light curves. As you can see in the right panel, the black is from the XRT and the red is in the optical, and something like achromatic light curves are very hard to observe uh, in case of Swift. And as you see, most of the breaks in the light curves are chromatic. They haven't been achromatic anymore. And this chromaticity in the light curves tells a lot about the nature of the Howard shock emission and what kind of model and what kind of progenitor might be. So coming back to the energetics of GRBs, uh, cases where we are able to measure the jet opening angle either from optical or from radio data or through multiband modeling, um, it's possible to convert the uh, isotropic gamma ray emission to correct it for the jet opening angle. And what we have seen is that probably the gamma ray energy is clustered around 10 to the power 51 ergs, as you can see in the Gaussian peak is around 10 to the power 51 ergs. And if it is true, then this was the point where people thought that this will be a good candidate. GRBs will be a good candidate to use for the cosmological probes if at all the energy is clustered and if it is a standard candle. It has not been established yet, but in most of the cases, peak of this energy distribution is lying around 10 to the power 51 ergs, and that's where we have thought that probably they can be used as standard candles. And we put all the energies together and compare with this local supernova type 1 BC, whose energies are clustered around maximum 10 to the power 48 ergs. The GRBs are lying at much higher end, and although there is a dispersion and there is a broad um, um, distribution of energy, most of the clustering is still around 10 to the power 51 ergs, even in the Swift era, and some of this intermediate GRBs have been shown in the dotted line, and which are in between the supernova and the main GRB distribution, and that's what we are trying to understand, if there is any continuum which exists and which can be helpful to understand and to decipher the nature of such energetic explosions. Possibly there is a continuum which is making such a distribution, but a lot more is required to be understood. In this plot, you see that with redshift how the energetics are varying, and you see that with the red dots, all the black GRBs have been shown. And with the redshift, they have been always at the higher energy end. So lat detected GRBs are more energetic in gamma rays, whereas shift distribution in general less energetic. But there is a big range still in the apparent isotropic energies are Swift and what has been seen from that so far. So there is still a question that do Fermi-Lite GRBs have apparently smaller opening angles, or why the isotropic equivalent energy of black GRBs are high? This is still a question. A lot more observations are needed to know more about these kind of GRBs. Coming back to the third part of the lecture, which is the possible progenitors and the cosmological implications. We know that many kind of possible progenitors have been proposed, and we saw in the animation also that probably the binary neutron-star merger, or maybe collapse of the very massive star, or maybe a black hole white dwarf merger, black hole neutron-star merger, all can produce a system where centrally accreted black hole creating bipolar relativistic outflow can be produced, and that's what is the system which have been suggested as a possible progenitors for these CRBs, whereas collapse of massive star are more towards long duration GRBs, whereas collisions of binary neutron stars is favoring more towards the possible progenitors for the short duration GRBs.